distinguished paper.
Yes. Thank you for the introduction. So thank you also everyone for coming. Today we're going to talk about Undef, why we no longer want it in LLVM, and how we can remove it. So to give you some context, currently Alive2 finds about 136 miscompilations in the LLVM test suite. 25 of these tests will become correct the moment Undef would vanish from LLVM, which is about 18% of the total failing tests. Notice that these tests are only unsound because Undef exists, even though the majority of the tests do not touch Undef explicitly. Throughout the years, the LLVM community has managed to remove about 58% of total Undef uses, but currently progress has plateaued as the remaining, almost all the remaining users of Undef are concentrated in loads of uninitialized memory. So what actually is Undef? So as many optimizing compilers, LLVM has two kinds of undefined behavior. The first kind is immediate undefined behavior, which is reserved for operations that trap the CPU. Deferred undefined behavior covers all the remaining cases. So LLVM has three main forms or values to represent deferred UB. So the first form is poison, as you can see there, which is sticky and propagates like floating point nans. The second form is Undef, which is mostly used nowadays to model loads of uninitialized memory. Notice that every time we read an Undef value, we may get a new different value. Freezing a poison or Undef value gives us a non-deterministic but fixed arbitrary value through the freeze instruction. Then, at the bottom of the lattice, we have regular values. Notice that from these values, only poison is sticky, while Undef is not. This non-stickiness of Undef gives it some counterintuitive properties. So, for instance, consider here this optimization where we want to transform 2 times y into y plus y. So, many of you here might think that this is clearly a valid optimization. However, it is actually not, only because Undef exists. To see why, remember that every time we read an Undef value, we may get a new different concrete value. This means that in the program on the left, we have a single, if we consider y to be Undef, we have a single Undef read. So we get an arbitrary value, we multiply it by 2, so we get an even number. However, in the right side, we have 2 Undef reads, which means that we read Undef twice. The first read could be, for instance, 2, and the second read 1, which gives us 3, which is an odd number. So we went from a program which gave us only even numbers to a program which gives us both even and odd numbers. So the refinement is clearly not valid. So if Undef can cause these subtle bugs and get in the way of optimizations, why is it still here? As I mentioned already, the remaining uses of Undef are almost all come from uninitialized memory. We want to change uninitialized memory to poison. However, we first must address 2 main blockers. The first blocker are bit fields. So Clang currently uses a read mask write pattern to write and mask bit fields. And if we change uninitialized memory to poison because of poison stickiness, this pattern breaks. The second problem are raw memory copies, which are currently unsound in LLVM. Changing uninitialized memory to poison would further aggravate this problem, as we would get more poison values in memory. So that's not something that we want. So let's now explore each of these problems in more detail. So the first blocker are bit fields. So to store bit fields, Clang reads the whole word, masks it, and then writes it back to memory. So in this example, we have these bit fields, and to write to bit field A, we load the 32 bits, then we clear A's bits, and then we store the value back to memory. Today, this is correct because Undef is not sticky. So, because poison is sticky, if the original load contains a single poison bit, a single uninitialized bit, the whole load will be 32 bits of poison. Then we end up storing this poison value to memory, which overrides the existing bit field values. The second problem are raw memory copies. So LLVM currently lowers small mem copies to integer load store pairs, as you can see here. This has two main problems with using integers. So the first problem is that pointers in LLVM are not mere addresses, but also carry something that is called provenance. So provenance can be thought as the capability to access a memory region. So the problem with using integers is that integers do not capture this provenance. So if we load a pointer through an integer type, we end up discarding this provenance. The second problem is that poison is value-wise in integers, which means that if a single bit in memory is poison, the whole loaded value will be poison. This conflicts with memcopy, as we want to copy memory as it is without spreading poison bits. So switching an initialized memory to poison would increase the quantity of poison bytes in memory, which would make the raw memory copy problem even worse. So both these blockers boil down to the same problem, which is that LLVM cannot represent raw memory in SSA registers. So that's precisely our first contribution, which is a new byte type that can represent raw memory bits in SSA registers. Additionally, the byte type tracks poison per bit, which means that a single poison bit does not taint the loaded value. So previously, memcopy intrinsics were lowered to integer load store pairs, as you can see on the left. And now with the byte type, we preserve individual poison bits and pointer provenance. We also added a new bytecast instruction, which allows us to convert byte values to other types, perhaps integers and pointers. So the bytecast instruction comes in two variants. The type panning variant forces reinterpretation of the bits, and the exact version on the right returns poison if the type of the value encapsulated by the byte does not match the cast destination type. So for instance, consider that B8 value represents a single pointer byte. If we try to cast that pointer byte to an integer, we get poison back. So the byte type gives us more than just a sound memcopy lowering. Consider, for instance, this char type in C, which acts as a universal type holder. So it can hold the raw bytes of any given object in C. Also, char pointers can alias with anything, which is what allows us to write a memcopy implementation. So on the left, we see that we copy a single byte as we would inside the manual memcopy implementation. Currently, char lowers LLVM lowers the char variable, the char type, to integers, which is unsound because of provenance and spreading of poison bits. And with the byte type, we can preserve the raw bytes without coercing them and casting them to integers. Another application of the byte type is to fix existing optimizations. Consider, for instance, load widening, where we merge two consecutive loads into a single one. So the original code loads two values from consecutive memory locations. In the middle, we show the emitted IR by LLVM nowadays, which widens the load and then uses bitwise operations to extract the two load results. Combining the load is unsound because of poison. So if either of the original loads contain a single poison bit, for instance, if load 1 contains a poison bit and load 2 doesn't, the widened load will be 16 bits of poison. So in the optimized program, the first load and the second load will be poison. while in the first program, we get the first load with a valid value. So this is not a valid refinement. With the byte type, we can just load the raw memory because poison is tracked per bit, and then use the bitwise operations and the bytecast instruction to extract the relevant parts. Our second contribution is a freezing load to address the bit field issue, which is equivalent to loading raw memory, then freezing it per bit, and then casting the results to an integer. So this is what bit fields need. Clang currently has 2 encodings for bit fields. It has a fine-grained encoding, which aims to reduce the bit width of loads, and default encoding, which loads at the word level. So these 2 encodings should stay ABI compatible, and if we freeze the loaded value per bit, we avoid this poison spread. So when we write back to memory, we don't overwrite other possible existing fields. So yeah, with the freezing load, these 2 encodings stay ABI compatible. So we ran a live 2 over the LLVM test suite with our new 2 contributions and found that 11 of the previously flagged tests were fixed, which is about 8% of those I mentioned at the beginning, and we had no new failures. These tests include unsound memcopy lowings and unsound pointer coercions. We also verified the compilation of real C programs with the live CC, and we found that in Draco, 330 memcopy lowerings were fixed, 1 for eSpeak, and in all the benchmarks we analyzed, no new issues were reported. We also evaluated our benchmark across 20 applications from the Phoronix test suite, as you can see here. So here you can see 2 plots. On the left, we have the runtime performance, and on the right, the compile time performance. So notice that negative values here are better, and the average value is indicated by the dashed line. So with our new optimizations implemented on top of the byte type, the worst slowdown we have in runtime is around 4% in SIMD-Johnson, and the average is about 0.8%. Compile time stays relatively unchanged with an average regression of 0.2%. So we analyzed the emitted bytecasts in our code and found that most of the bytecasts follow a really simple pattern, which is we load raw memory and then immediately cast it to another type, for instance, an integer. The Rust folks expressed some interest in allowing loads to do the type panning, which would allow us to combine this load bytecast pair into a single load to the target type. So we benchmarked an implementation and found that 1.6% of the old instructions in the old version were bytecasts, and this fold changed the number down to 0.1%. So here are the results with the new folds. We see that average runtime regression reduces to 0.2%, and compile time stays largely unchanged. So regarding the SIMD-Johnson regression in runtime, we investigated and found that it is due to jump threading not able to combine some basic blocks that it could previously. We found out that this is due to LLVM's range analysis not being able to operate on the new byte type, only integers. So extending the analysis to operate on byte types as well would resolve this regression. Lastly, we benchmarked an implementation where we switched an initialized memory to poison and lowered the bit fields through the freezing load. So the average regression and compile time impact here are about 0. And the largest regression we observed was in runtime, I believe John the Ripper, with around 1.5%. We traced this regression back to a loop alignment heuristic, which reacted to some small code changes, not necessarily to our new semantics. So to conclude, we introduced a new byte type and a freezing load. Together, they allow us to change an initialized memory from Undef to poison. Also, the byte type fixes some additional issues with LLVM and raw memory semantics, fixing some of the LLVM test suite tests and some miscompilations. Furthermore, it has negligible performance costs. And to conclude, I'd like to mention that we started upstreaming the byte type to LLVM, and the first patch has already landed. So, thank you.
Questions?
This is really cool stuff. When you got to the bit field stuff, I was kind of expecting you to say you were going to load it as a byte and then add byte and an OR operations rather than the approach you took. Did you consider that?
Yes, so the freezing load that we use for to load bit fields is actually a syntactic sugar for what you were mentioning. So a load of a raw memory type, a load of the byte type, and then a freeze, an explicit freeze, and then a cast to an integer. So we believe that if we did introduce those three instructions instead of a freezing load, the IR instruction count would increase for bit fields. So that's why we exposed the freezing load attribute.
Okay, sorry, I meant if you added and an OR to be things that could also take bytes rather than integers.
Okay, yeah. So you mean extending and an OR to also operate on the byte type. Yeah, that's a little bit tough because so bytes can hold both integers and pointers. So the semantics of an and OR instruction on pointers are not really defined because pointers have provenance. So we don't really have a good semantics to a concrete semantics to extend those instructions to the byte type. So that's why we didn't.
So strictly speaking, this is semantics change of the current LLVM specification. Have you assessed any thoughts on the impact on the other project which compiled to LLM, try to reason about semantic preservation and stuff like that?
Yeah, I'm not really familiar with, so I can't really say much about it. So yeah, sorry.
I guess maybe more just a remark than a question, but having worked on a verification system that worked at the LLVM level, this was a persistent pain in my ass. So thanks for working on this.
Yeah, thank you.
One last question.
Hi, thanks for the talk. If I remember correctly from the beginning, you said that removing Undef would fix about, what was it, 18% of miscompilations from the test suite, whereas at the end you say that your fix fixes about, or with your changes, about 11% of miscompilations.
Yes.
So what about the other ones?
Yes. So the byte type was like so the initial goal of the paper was to fix the raw memory issue in LLVM. So one consequence of the byte type is that we can also model the bit field loads, which is one of the main obstacles to remove Undef. So these tests that I mentioned on the byte type, they are not included in those tests that would vanish if Undef was removed. So they tackle things like unsound mem copylowings and unsound pointer coercions. So we actually haven't removed Undef yet because we need the freezing load as well, and we started upstreaming the byte type. So those tests are only concerned things like unsound pointer coercions and raw memory accesses. So those are meant to be fixed with the next patch, which would tackle the mem copylowing. So yeah, in the long term, those 18% would vanish, yes.
Okay, let's thank Pedro.